Okay, so we're going to go back to comparators. So the last thing that we looked at yesterday were the subtractors, the half subtractor and the full subtractor. You know, you were the homework, you had to continue with this. And again, I'm extending the homework, all of the outstanding homework deadline until after 4th of July, right? So you'll see the links appear on Gradoscope with due date. I guess it's going to be the morning of July 6th, right? Because Monday is 5th, we're off. So by Tuesday, we'll want all of it. The next topic is the comparator circuit. So let's look at that. So now we know how to add binary numbers. We know how to subtract binary numbers, right? We actually know how to build a circuit. Now we're going to learn how to build a circuit to compare two binary numbers. They can be either equal, or one can be greater or less than the other one. So we're going to, for example, take 3-bit binary numbers. But if they're larger or smaller, it will be analogous. So if the first number is A and the second one is B, then we can look at the individual binary digits, right? So from the least significant, and this is going to be A0, B0, to the most significant, A2, B2, right? Important that you understand that we're talking about here individual digits that compose these numbers. Okay. Now, let's define the function, right? So this is the equality function. And the equality function is going to be equal 1, right? It means that the equals is when this equality function is equal 1, which means that A is equal to B, right? So the equality function will be 1, true, only if A is equal to B, which means that all of the digits of A has to be equal to all of the digits of B, right? But because we have to do it bit by bit, right, we're going to do this individually, right? So in order for A being equal to B, we need each element, each of the digits be equal. So let's start with the most significant one, A2 and B2. So they're equal if A2 is 1 and B2 is 1, right? So that will be 1. So A2 and B2, right? If both of them are 1, we can say that A2 and B2 together they're going to be 1, and the function is going to be true. Any questions at this step? Can people still hear me? Who can still hear me?
Yes.
Yeah, okay, good. So that's one possibility for the equality to be true, but there are more. So we can say that A2, B2, or if both of them are 0, right? They're equal as well, right? If A0 and B0, so that will be fine too. So it will be A prime and B prime, right? So if either of these are true, right, A2 is equal to B2. Questions? Now, of course, we need to figure it out for the whole number, not just for this one digit. So for the whole number to be true, equal, right, these two digits have to be equal, but the rest of them also have to be equal, right? So we're going to put this in parentheses, and then we'll have the multiply sign, right? So we need to now worry about A1, right? So A1 has to be, so A2 has to be equal to B2, but A1 also has to be equal to B1, right? So that'll be in the second parentheses. But it will work the same way, right? They're analogous, right? For each individual digits, let's say AX, BX, or AX prime, BX prime. Any questions about this? So this is for comparator function to be 1, for them to be equal. This has to be true. If not, If even one of them is not equal, the whole thing is going to be false. So that was pretty simple. Now we need to look at two other possibilities, right? Or two other possible functions when we compare numbers. It could be greater than or less than. So let's look at the less than function first. So the less than function is going to be 1 if a is less than b. Otherwise, it's going to be 0. A less than b. Okay, so if we dissect it bit by bit, right, in order for one possibility, or actually sort of like the quickest way to determine if a is less than b is for a2 to be less than b2. Right? And the only way that that would be possible is for a to be 0 and b to be 1. Any questions about that? Right? So we can just say not a and b. Right? So whatever other digits are, right? If it's not a and b, then yes, the whole thing is going to be a is going to be less than b2, right? No matter what the less significant bits are. If the most significant bit, a is less than b, then a is less than b. Okay, so do we have it? A is 0, and right. So these are just equivalent. So we can say that a2 is less than b2, or they could be equal, right? And if they're equal, we're going to just copy the expression from here, right?
So is this less than or equal to, or not just strictly
no,
less
this
than?
this is less than, right? So look, if you can think of it in terms of short circuiting, if a is less than, if a2 is less than b2, then we're done. This whatever else we figure out. But if a2 is less than b2, that will be enough for the less than function to be 1, right? No matter what else happens, because it's connected with OR, right? We're ORing a bunch of things, and it's a sum of products, right? And this first product, or this first term, if it is true, if it is 1, right, it is guaranteed that a is going to be less than b. Does everybody follow that?
Yeah.
Okay, good. But what if a2 and b2 are equal? Does it mean that the whole number is equal?
Not necessarily, because
Not necessarily. Yeah, because we have a1 and b1, a0 and b0, right? So there is another possibility. So let's say that this is false, right, if they're equal. But then we need to consider what happens if the first bit is equal, but the rest of them are not. So first we're going to express that the first bit is equal, that a2 is equal to b2. Put it in parentheses, and now we want a1 to be less than b1, right? So if a2 is equal to b2 and a1 is less than b1, a is going to be less than b. Does that make sense? So a can be less than b with just a2 being less than b2, or a2 and b2 be equal and a1 is less than b1, right? So how do we express that? So we say that a2 and b2 are equal, but I'm sorry, I messed it up. But a1 is less than b1, right? And we know well that the English word but in Boolean logic is what kind of operator?
And?
It's and, yeah? So let me get back to where we were. I didn't mean to quit out. Sorry. You can keep asking me questions while this is loading.
So this is the way things worked, in the beginning of time. Is this the way? You know what? Forget it. Sorry.
No, please ask. Go ahead. Continue. Yeah. What do you mean?
So the basic circuit we saw the other day, the IBM full adder, is that the way things still work?
Yes. Oh, well, look, the implementation, their full adder is probably implemented differently, but the logic still works, or their old full adder still works. So everything that we're learning here is, made up. It's abstract, and in that sense, it is still true and will always be true, right? Because it's a, logic. It's a language. It's a highly formalized language that was, invented, right? And then you can use this language to design a circuit and, make it, and it's going to work the way you designed it because that is how you designed it, right? So, they call this computer science, but we're not studying the world, right? We're not studying, physics or chemistry. We are not doing like empirical research on, on trying to, classify and, come up with a theory that explains some kind of real phenomenon, right? This is, this was like pulled out of one's finger, and it's true of mathematics as well, right? It's mathematics is not discovered, right? It's invented, I don't know if that puts it in perspective, Anyway, so deep thoughts. Okay. No, really, was this helpful?
A little, thank you.
A little, okay, not very helpful. I can only try. I mean, the point was that these things work by design, right? This is how they're designed, and that is why that's how they work. Those axioms for Boolean algebra, right? The whole point of an axiom is that it doesn't need proof. Yeah, you establish it, you decide, oh, this is how this whole thing is going to work just because I decided that, and then based on the axiom, I can come up with theorems and properties, etc. Right? So just to, I don't know, give you maybe another parallel example. Let's say with geometry, right? You have, you all studied geometry at some point in probably middle school or high school, and there are 5 axioms, by Euclidean axioms, and then based on those axioms, the rest of geometry sort of is constructed, right? And one of the axioms is that 2 parallel lines never intersect, right? I think it's the last axiom. But you can have a different kind of geometry, right? Non-Euclidean, like there is geometry of Lobachevsky, where you get rid of that axiom and 2 parallel lines can intersect or something like that, right? And whenever we come up with these, formal languages of math, like for example, geometry, right? Even though it's made up, it is useful because it does reflect our experience in the world, the way we experience it. And based on that, we can use it in conjunction with other scientific knowledge and I don't know, build mechanical things. So this geometry of Lobachevsky, and there are many other geometries, right? It seems completely hypothetical, right? Because they say, well, of course, in the real world, parallel lines don't intersect. But in fact, it turned out to be useful later on in the study of, I don't know, like general theory of relativity, because when you have when space becomes distorted, right? Then parallel lines, now start not being parallel anymore, right? Same thing with George Boole. He came up with these completely hypothetical, completely abstract, logical concepts, right? This, Boolean logic, and he was just doing it, I don't know, to fill time. I don't know. But then later, 100 years later, or something like that, people say, oh, we can use this, right, to design circuits to build computers. Anyway, okay. So in order for A to be less than B, A2 can be less than B2, and that's done, right? Its own term. Then we have or, another possibility. A2 is equal to B2, and also, right, now A1 has to be less than B1. So we have to put it in parentheses and multiply them. Now, what does it mean for A1 to be less than B1? Just like with B2, it's going to be not A and B, right? A is 0, B is 1. Okay? So this whole thing is now the second possibility. Okay? So A can be less than B if this is true, or if this whole thing is true. Okay. But there is another possibility, right? The other possibility is going to be that A1 is equal to B1, just like A2 is equal to B2. Right? But there is still a chance for A to be less than B, and that will be that, yes, A1 is equal, A2 is equal to B2, A1 is equal to B2, but A0 is less than B0. Right? So let's try to express that. So we're expressing, we're saying that A1 is still equal to B1, but now we want to express that A0 is less than B0. And again, it will be the same as in the first two cases. It's not A0 and B, right? A must be 0, B must be 1. But
Question.
we're not done yet. You go ahead with your question. Yeah, we're just, we're not finished yet.
Oh, I was gonna say, isn't there another condition where like A2 is equal to B2 and A0 is less than B0?
But that is what we're expressing right now.
But the A0 less than B0 is connected with an OR.
Yeah, the formula is not complete. You know what? Hold your question. Maybe once I finish, maybe it will become clear. Or if not, you ask it again. Right? We need these parentheses here, right? Because this only matters, right, if A2 is equal to B2 and A1 is equal to B1, right? So that's why we need the parentheses around this whole term, and we need to multiply them. Does that make sense? Or does that answer your question?
Yeah, thank you.
So, but let's go over it, right? Let's go over the, the precedence of these logical operators. The first possibility is the simplest, right? It's then the most significant bit is less than, and that's it. Then we have or, and then this whole thing, right? Well, this whole thing says that the most significant bits are in fact equal, and at the same time, this whole thing, right? And within this whole thing, two possibilities. A1 could be less than B1, and that would make this whole thing 1. And with this 1, it will be 1, right? Or A1 and B1 can be equal, right? So at this point, in this complex compound, relation or expression, we got to the point where A2 and B2 are equal, and A1 and B1 are equal, but A0 is less than B0, right? And that expresses all possibilities of A being less than B. Right? If none of these true, which would only happen when they're all equal, so let's say that A is not A and B is false. That would happen if the whole numbers are identical, right? Then this whole thing would become 0, right? Sorry, and that would be also 0. So basically, all of them are equal to each other, so there will be no ones in. Means that this will be 0 because A2 and B2 are 0, and this whole product is also going to be 0. Questions about this? So the assignment related to this would be to do like the opposite, right? It will be extremely similar to express f being a is greater than b, right? It's going to be sort of the reverse of that, right? So that will be the assignment based on comparator. Please take a screenshot of this for the assignment.
Sorry, I'm a little bit confused. So when A prime 2 and B2, when A2 is 0 and B2 is 1, that means F would be 1 if that condition is satisfied?
That's right. So that is exactly right. If A2 is 0 and B2 is 1, then this function is satisfied entirely, right? This already means that A is less than B, and because it's an OR here, like the rest of it can be completely ignored. It doesn't matter.
And if we're looking at it from the right side, where if A0 is less than B0, can we ignore the rest, or?
Well, the thing though is that you would not look at it from the right side, right? Because on the right you have least significant bits, right? So you would always start with the most significant bits, right? So let's say that you want to compare two decimal numbers like, 345 and 576, right? So it doesn't matter that like what the 45s and the 76s, 300 is less than 500 and you're done, right? You're looking at the most significant digit. However, if the first digit is the same, then you go on to the next less significant digit, the next most significant digit.
Oh, okay, that makes sense.
Good. And does that make sense to everybody? Right? When we're comparing two numbers, we start with the most significant digit, right? If we're looking for less than, greater than, and they're different, immediately we have our answer, right? Only if those first digits on the left are the same, we will go to the right one by one until we find the first inequality, and that will give us the answer, and we can ignore all of the less significant bits. And that's what we're doing. And of course, with if you have more bits, more digits, then this expression will get sort of like more. Here we have two large terms, right? The second term only makes sense to us if we can assert that A2 and B2 are equal, right? Because if A2 and B2 are not equal, right, that takes us back to this situation. You may need to sort of like look at it again and again, just on your own to get it to sync. And I'm not sure how else I can explain it. Right? These have to be distinct possibilities, right? So one possibility, I'm just going over it again in different words. One possibility in order for okay, let's just do it here. I don't know what happened. One possibility for A to be less than B is simply for A2 to be less than B2. And that is the shortest here, most concise term, right? And if it's 1, then the function is 1, right? A is less than B. But now, let's say that A is not less than B. Maybe A is greater than B. Or whatever it is, right? Well, so if if A is greater than B, let's say if A is 1 and B is 0, then this would be immediately false. And then we need to look at this other possibility, right? But if A is greater than B, then this whole thing should be also false. And we will assert that by saying that we would only continue looking at A1 and A0, etc., only if A2 and B2 are in fact equal, right? So this is why we need to have this term here multiplied by the rest of it. Does that make sense? You know, as I said, if we're looking for A to be less than B, sure. The quickest thing is that if A2 is equal to B2, is less than B2. But only if A2 is equal to B2, we want to keep going. But if A2 is greater than B2, then we don't need to keep going. And to establish that, we say that, oh, we care about what happens afterwards only if A2 and B2 are equal to each other, right? If A is greater, then this will be false, right? And because we're multiplying, the whole thing will be false. Does that make sense? If it doesn't, try to ask me about it. Okay, it makes sense. Good. So we're done with the comparator. Again, if you haven't taken a screenshot, please take a screenshot, and I would like you to come up to a similar formula. It will be very similar for A being greater than B as opposed to less than B. Okay, good. So now let's go to the next topic, controlled input. Let's stay here. Okay, there we have it. Oh, we don't want skip. Sorry, we don't want to see that. No. Okay. Sorry about that. The wrong slide. Okay, so we're going to look at circuits for devices called controllers, and the general topic is called controlled input. All right, so here we have a problem. Let's say that we have a circuit, and A is a line in, one of the inputs, but it is external, right? So we don't know its value, we can't control it, we just don't know what it is. Right? But in our circuit, Y is the output of this control circuit. Right? And the control part of it, we haven't seen that yet, is when we're going to influence the circuit. It's sort of like a dynamic circuit rather than being, sort of like frozen in the way it works, right? The control circuit, in addition to having regular inputs, will also have a control input, or more than one, that will change its behavior. Right? So for the output, so we have a single unknown input A, and we have the output Y. And we need our control circuits to sometimes produce Y equal to A, and sometimes produce Y not equal to A. So we use this control line called C. Now, what is special about control is that we use the control line or multiple control lines as input, and not the external input, which we want to control, in this case A, when setting the truth table, right? So the truth tables for this are going to be weird at first, right? So let me show you what I'm talking about. So in the truth table, though A is technically the input, but because it's unknown and we cannot control it, we're going to use the control line as input, and we can control it. So our C, our control, is going to be 0 or 1. And we almost don't care what A is, right? It's just that when C is 0, right, when we don't send control signal, then A will just go directly into Y, right? So if A was 0, Y will be 0. If A was 1, Y is 1. But if we send a control signal, we're going to flip it. We're going to change. Whatever A coming in is, Y is going to be the opposite. Any questions about that? Right, this is like the simplest control circuit. So let's try to express it as a function, right? Well, as a function, the outcome Y is going to be not C and A, or C and not A. Make sense? Okay. So this is the expression of the function of this control circuit. Now we're going to draw a diagram. So just a quick note about, particularly about the final exam. In the problems for the final exam, some of them will ask you to draw a diagram, but usually there will be several steps, and the last step will be to draw the diagram. You should always do all of the other steps before drawing the diagram, because I will try to give as much time as possible, but in fact, if one runs out of time, and in a particular question, they did all of the formulas and conversions, and didn't have time to draw the actual final diagram, you'll still get most of the credit, right? So the diagram itself should be done the last, unless that's the only thing you need to do in the question. But in a question where there are several steps, do all the other steps first, and only draw the diagram if you have time, because the diagram will be worth fewer points than the rest of the question, if that makes sense. In any case, this is the diagram for this function. Let's quickly decipher it. So we have a sum of products, and there is our sum. There is our OR circuit. Yeah. So that's the one that if you sort of decipher it top down, right, then this plus this OR is going to be the closest to the output. Oh, by the way, with all of these circuits, right, whenever we finish drawing them, we must put a rectangle around them, meaning that once it's done, we can seal it, and it'll just work, and we don't need to worry about what's inside. Okay, so there we have our line in. It is the input, even though it's unknown. So the outputs are always on the right, the inputs are always on the left, and the controls are always going to be coming from the bottom, right? And though A is input, for our purposes, we can control C. So in the truth table, we'll have, the C, which we can control. Okay, and in order to produce this, right, it's not C and A or C and not A. So there is the OR. So this will be not C and A. Okay, so there is the A coming in straight, and there is the C coming in through the inverter. So A and not C. Okay, we got that one. And here we have C and not A. So here the C splits, and it goes straight into the AND. And the A splits there and goes also into this AND, but through an inverter. So we got not A. So this circuit makes sense. So everybody, if not, quickly ask me. Right. So when we draw circuits, that you're like literally converting every operator, right, into a gate, right? Every complement will become an inverter. Every plus will become an OR gate. Every multiplication sign will become an AND gate. Yes, question.
So when we create the circuit, you want us to always box it like that?
Yeah, you basically first draw it. When you're done drawing it, put a box around it. Right? And then your inputs are going to be on the left of the box. Your output is going to be on the right. Outputs, possible multiple outputs on the right of the box. And your controls will be below the box. Okay? Okay. I don't know, on the final exam, if you do everything right and you forgot to put a box about it, I'll still give you all of the credit. But, that's the idea, okay. Like, I'm not going to, demand the box to trip you up. I mean, it's just logically, it makes sense. Okay, let's continue. So here we have a more difficult problem. You have the A, the external input that we can't control, and we have an output, Y. But now there are more possibilities. Yeah, the input is still just a single unpredictable input, but the outcomes we want to have a more fine control over, right? We want to be able to just express A as it is, just continue. We want to be able to flip it, but we also want to be able to have deterministic outputs. We also want to be able to switch it so that it's 0 no matter what A is, and then we should also be able to, we must also be able to switch it so that the outcome is 1 no matter what A is, right? So we have, rather than having 2 possible outcomes, okay, this is taking too long. Rather than having 2 possible outcomes, A or not A, we will have 4 possible, four possible outcomes: A, not A, 0, and 1. Right. So let's see. And we need to be able to switch between these 4 possibilities using some control inputs. So before I go further, would a single control input be enough, or would we need more? Because the controls can only be 1 or 0. So in the previous one, we could switch. 0, it's the same, 1, it's switched, or whatever, right? But now, we want to have 4 possible outcomes. So is 1 switch enough for?
No, we need 2 inputs.
2 switches, right? We need 2 control inputs, right? I think that's what the student said. You need 2 control inputs, 2 switches, and by using different combinations of these 2 switches, you can come up with 4 outcomes.
So, Professor, I think your voice is like lagging out.
Oh, I'm sorry. Can you still see the picture?
Yeah, we can see the picture.
For me.
Okay. How's my voice now? Is it better? No.
No, it's not very clear.
I think I know what we can do to improve it. I'm going to turn off my video because that takes up bandwidth. So the heat wave is over, right? But now it's raining. How's my voice now? Is it getting better? Can you hear me at all?
Yeah, I can hear you. But now the screen is frozen.
It's frozen?
Yeah.
Okay, I'm going to disconnect and reconnect. So stay there, don't leave. Okay, I'm back. Can you hear me now?
Yeah, we can hear you.
Okay. So let's try to share this screen. Do you see the screen change?
Yes, as problem.
I'm sorry. It does change?
It only says controlled input and problem for us.
It's not changing.
No.
I'm going to try to connect through my hotspot. We have time, no rush. We have time, so let me set my hotspot. Okay. Um, can you still see my screen? Um,
Yeah,
still
we
hear
can
me?
see it. Yeah, we can still see it's the same screen.
What does it? You just see like control input and problem?
Yeah, the same thing.
Okay. Okay, so I'm going to unshare and try to share again. So stop sharing. Share. So I'm on my cellular data now. Share screen. Do you see anything? No. Oh.
It's no, not yet
Do
for
you
me.
see? How about now? Do you see the video feedback?
Yeah, I see the video of,
Okay.
the video.
Okay, good. So that bodes well. So let's try now. Are things moving on the slide?
Yes, now it's moving.
Okay, good. All right, so yeah, so as I said, we need two control lines to create four possible outputs, right? So we have four outputs we need, right? So we will need two controls. And we'll call, instead of calling them C, we'll call them alpha and beta, right? And again, we don't know what A is going to be, right? But we just want to express four possibilities of our two controls, right? Imagine that they're like two switches. They can be both off. One of them can be on, the other off, the other way around, or both can be on, right? So our truth table will have four lines. And then it doesn't matter what combinations are which combination does which. So we could do it in any order, but let's do it in this order. We will produce 4 possible outcomes. Could be A, could be the reverse of it, could be 0, and could be 1. Okay, so we're just assigning outcomes to the combinations of inputs. Okay, so now we're going to express a function y based on this, right? So y is going to be A in our arrangement if A and B are 0. So not A, not B, and A. Okay. I'm sorry, not alpha, not beta, and A. Then we're going to have, let's see, y is going to be, let's look at the other one, not beta. I'm sorry, not alpha, beta, and not A. The third possibility is going to be alpha, not beta, and 0. And quickly, what happens to this input alpha, not beta, and 0?
Anything times 0 is 0, so you can.
Yeah, it goes away. Yeah, it disappears. And then the last one, we have alpha and beta and 1, right? So what happened to the 1 here?
I mean, anything times 1 is itself, so.
Yeah, that's right, identity. All right, so what is left is our y function. The way we set it up is not A, not B, not alpha, not beta, and A, or not alpha, beta, and not A, or alpha and beta. I think maybe I went too fast. It actually will become clearer here. So now we can go back to the previous one, but let me just try to push in more. Now we will have, instead of having just one external input, we'll have 4 external inputs, multiple external inputs. And when we have such thing, we would call that control unit, we would call it a multiplexer. So we have multiple inputs. These are all external that we cannot control, and a single output, right? So it's going to sort of like multiply everything. So the way these inputs are going to be arranged, that at times the first one of them is going to have, you know, a signal, and the rest not. Then at other times, the second one will have signal and the rest not. At other times, the third one, and at other times, the last one, right? So 0, I0, 1, 2, and 3. So how many controllers do we need to create the 4 different outputs? Right, so before we had a single input, but now we have 4 inputs, but we still have a single, well, let's rephrase that. We need to create just 4 different outputs. Right? So like last time, the outputs were, you know, A, not A, 0, and 1. Here, it's going to be similar. But in any case, it will be 4 different outputs. So how many controls we need to create 4 different outputs? Right? That's the question. All right. Well, 2, right? Same thing. 2 controls, alpha and beta, or maybe you can call it C1 and C2. Right? It doesn't matter how many inputs there are. If you want to produce 4 different outputs, you need 2 controllers. So in this case, rather than calling them alpha, beta, C1, C2, we'll call them S1, S2, because in conjunction with the term multiplexer, the controls are called selectors. And in fact, what you will see is that you're effectively selecting the inputs. So let's see. here we have our two controllers or selectors, S1 and S2, and they will produce 4 possible outcomes, right? And what we're calling them selectors because effectively we're selecting one of these inputs to become the outcome, right? So in a way, these are literally switches, right? Where switching between different lines. So the outcome, the y, can be either equal to I0 or I1 or I2 or I3. Which one? Depending on the state of the selector switches. So if we express this as a function, as a Boolean function, well, we can express the state of y in the first line as not S, not S2, and I0. The second one is going to be not S, S2, and I1. Then S1, not S2, and I2. And then S1, S2, and I3. Okay, so this is our y function, the function of the multiplexer. And this is, whenever you have a function, you can make a circuit, right? This may not be the simplest circuit, but it'll work, and it will work exactly right. So what we have are the 4 inputs, all leading sort of into the same output, but passing through our switches, right? So this is, these are sort of like min terms, like them. So where you have a sum of products, right? That means that the results of all of these products are going to go into this big OR gate. That's the sum. And then each one is a product, right? So there's 4 of them. 1, 2, 3, 4. And each is a product of its own line in, either 0, 1, 2, or 3, and both of the controllers, right? So that you will see that, we have 4 wires going to the OR because there are 4 products. But then within each product, we have exactly 3 wires going into each end. Yeah. The inputs, the I's, are always true, identity, right? But the controls, the selectors, can be either, depending on the combination, true or false, right? So that means that, for example, this is S1, right? It will go true for I2 and I3 here, but it will go false, this is the inverter, to I0 and I1, right? And similarly, S2 will go true into I1 and I3, and it'll go false into I2 and I0. Okay, and there are plumbers working on the building, and I need to let them in, so I apologize for the interruption. I will be back in 10 seconds. Okay, I'm back. Let's continue. Any questions about this?
Do we have to put the plus on the OR gate over there?
you don't have to put it just as long as you make that curved line there and point at the end so that it's not the same, doesn't look the same as AND gate. Okay, so right, there is the S1 and S2, and there is the output, and then we can put a square, a rectangle around it, and now we have a multiplexer, right, where we have 4 lines going into it, and depending on how we put switches, we have the switches, one of these 4 lines is going to go out, right? So if like, for example, something like this doesn't necessarily need to be just Boolean, right? These inputs could be, well, anything you want. They can be video feeds, right? So when they have like live events with like multiple cameras, like a 3-camera setup or more than that, right? The director is sitting in the switching box, and you can instantaneously switch from one camera to the other, so that your, I don't know, TV show or sporting game that you're watching, it's actually a similar device like a multiplexer. Any questions? Okay, right? Because we actually don't care about what values of these are, right? We only care about which one we're going to send to the output. Is that clear? Okay. Right. So these control input circuits, they were different from the just gate circuits that we were building before. So you have to sort of keep that in mind. All right, now the reverse of this, demultiplexer. You have a single external input, and in this case, 4 possible outputs. Right? And these 4 possible outputs now are going to look different. We have sort of like a different looking truth table. Right? The 4 possible outputs could be the identity of I, true, in one output, the identity of y in the other output, the identity of I in the third output, and the identity of I in the last output, right? So what we're literally doing the opposite of what we did before. We had 4 input going in, we select one and push it out. Here, it's as if you reversed it. You have a single input going in, and you can switch it to send it into 4 different directions, right? It's like on a subway tracks or whatever, you can have a switch that the train goes into it, and then depending on how it switches, it can go either straight or to the left or to the right, or I don't know, down, up, whatever, right? Does that make sense? And then, of course, if you're sending this input to Y0, what are you sending to the rest of them? This should not be a hard question.
Not I?
Nothing. We're not sending anything there, right? Exactly right. We're zeros, right? So we're only, we're taking our input and we're sending it only to one of the outputs, and we send nothing to the other ones, right? Which is no signal, which is 0. Exactly right. Who was that?
Jordan.
Jordan, very good. So in some ways, these controlled circuits, they're maybe even simpler than the circuits that we looked at before, because here we're just sort of sending things in different directions, or sometimes we flip them. Okay, so how many controllers do we need to create 4 different outputs for the 4 different functions? Okay, hold on, let me close the door.
Still 2?
Yeah, that sounds right. So let's check if that is the case. In fact, right. So let's look how that works, right? With our 2 inputs, because it's multiplexer, demultiplexer, we're still going to call them selectors, right? And we have 4 different possibilities for combinations of selector states, right? Both off, on and off, or both on. Okay. And depending on these 4 different combinations, we'll send the output to one of these y's. So to express that, we'll say that y0 is going to be, is going to get the output only if it's not S, not S2, y1, it's not S1, S2. For y2, it's S1, not S2, right? And all of them need to be and I, right, to actually receive the signal, right? Because if we didn't have I, it would be just getting 1, right? But we don't want it to get 1. We want it to get whatever I is, right? So if I is 1, it'll get 1. But if I is 0, it'll get 0, right? So it's a product of all three, right? S1, S2, and I. And for the last one, so we have S1, S2, and I. Questions about this? Right, so we're redirecting or directing input and output, but we're actually not necessarily changing it, right? In one example, we had an option when we could set it to 0 or 1. But in most cases with control input, we're sort of like setting it around or reversing it. But often we could also, there should be a state where you just cut it off or set it to 1 always, right? So those are also possibilities. So the next thing is a flip-flop gate. And
excuse me, how would a logic diagram for a demultiplexer look?
That's a good question. I thought that I asked you to do that. Did I not? Why don't you draw it, right? It's going to look actually very similar to the diagram. Well, see, the problem, and it's not a problem, rather, but the thing about it is with multiplexer, you have a single function, right? Because you have a single output, right? With demultiplexer, you have 4 functions or 4 possible outputs, but you can still draw it as a single circuit. In many ways, the circuit is going to be, well, it'll look sort of reversed. I mean, internally it will not be reversed. Internally it will be, well, yes. So, okay, let's add that. Please take a picture of this slide, and this will be another assignment because you have a long weekend, and it will not take a lot of time. It will be actually quick and fun because you will use this as a starting point, and then you will draw the the circuit for that. It's just what will happen is that you will have a single I and coming in, and you will have 4 Y's coming out, right? And that single I would have to be split, right, into 4, right? And then each one of those 4, right, will have to somehow intersect with S1 and S2, right? And then for each one of those 4, produce 4 different outputs. So when you're done with this diagram, it'll in some ways look similar to this, but mirror image. Okay? So I'm reluctant to start flip-flops now because we only have 4 minutes left. So why don't you, we can start with flip-flops when we come back, because a flip-flop gate is a different thing. It's, I think I mentioned, it's a gate that can actually store memory, right? You can store a single bit of memory. So in a way, if you minimize them and you have, I don't know, 1 billion flip-flops, if you have 8 billion flip-flop gates, you can store a 1 gigabyte of data, right? So we'll start with that on Tuesday. But right now, these control inputs situations, they're kind of new. So any questions about them, right? So real quick again, This is the simplest control input, right, where it just passes you have one input, one output, and you can either pass it through or you can flip it, right? Sort of y can be equal to a or to the complement of a. That's the simplest control circuit. And then the next one was a more complex one where you have two controllers, alpha and beta, and you need two controllers because you want to, in addition to having pass through or the opposite, you also want to be able to set it to 0 or to 1, right, 4 states. Then the next one is multiplexer, where you're going to select one of the 4 inputs and send it out. Again, you need two controls or two selectors. And the last one is demultiplexer, right, which is sort of the mirror image of it, where you have a single input that you can direct in 4 possible outputs. Okay? Any questions about anything? Right, so before you go, I would like you to take screenshots of these 3 slides, right, because they have the homework, and I assign additionally, right, that I want you to draw the diagram for the demultiplexer. Again, it's not hard, and it will be kind of fun. Oh no, that won't help. Okay, so let me make it bigger here. Okay, so we want a screenshot of this. Okay. We want.
What is
Yep.
the homework on that?
One more time.
What is the homework on this slide?
No homework, but you need it for the second slide. Sorry, I just want you to take the screenshots. This one. So this is the first one. This is the second one. I will post these, but just so that you can get on it immediately. I'll post it after the plumbers leave. It's a mess here. This is the second one. This is the third one. And this is the last one. Okay, and I'll try to post all of the links by today. And just to go back to the outline just for a second, remind you the readings for the weekend. Right, we have some readings from chapter 4, 4.3, 4.4, 4.5. For the multiplexers, it's 4.11, right? And then next week, we'll do just 2 more things, the flip-flops and race conditions, and then we'll have a review. Okay. Any questions? Okay, if there's no questions, I wish you a happy weekend and happy 4th of July. And I will see you on Tuesday.
Professor,
Yes.
can I talk with you in office hour?
Absolutely. So as soon as I sign out, I will create an office hours session, and everybody who needs to talk to me, please come to office hours right now. Okay? Very good.
Happy 4th of July.
Happy 4th of July.